Hello all, in this lesson we are going to be studying electrostatics, which is, in short, it's how electricity behaves when it's sitting still. That's why it's got the statics part in it. We'll have a couple of equations to use, but mostly it's going to be concept. The bookwork associated with this lesson is 1 through 17 on pages 116 to 118. Of course, don't work on that alone. We'll do that together in class. And that should be the header of the first page of your classwork. And then right underneath that header, you should have the aim written, which is how do electric charges behave when they are at rest. Below that, please copy down these do now questions. I'd like to answer them in class with you next time we see each other. Alright, so let's talk a little bit about the structure of atoms. They're composed of three major subatomic particles. The first is referred to as a proton, and it has a mass of 1.67 by 10 to the negative 27 kilograms. That's on your reference table. The other is referred to as a neutron, and it has basically the same mass as a proton. This is also listed on your reference table. You'll also need to know that protons and neutrons exist together in the nucleus of an atom, that is the central area of an atom. Additionally, we have electrons, and their mass is very, very much lighter than the mass of protons and neutrons. You can find this mass on their reference table, but in chemistry class, you should know that it actually is considered to be a massless particle, but in physics we do give it this mass, 9.11 by 10 to the negative 31 kilograms. Keep in mind that not only do protons, neutrons, and electrons have mass, but they also have charges. You should know that protons and electrons have opposite charges, but that their charge is the same size. Now in chemistry, we would just use +1 for a proton and -1 for an electron. But in physics, we're going to use some different terminology. We're going to term both of these in terms of what we call the elementary charge. The elementary charge is symbolized with the letter E, and it has a quantity that goes with it as well. It's defined as 1.60 by 10 to the negative 19 coulombs. Coulomb is, in my opinion, just a bucket of charges. Much like this bucket of charges is being shown as being 1 coulomb here. It's just a group of particles, but in this case, the particles are the elementary charge. It could be protons, and it can be electrons, because the elementary charge is not specified as being one or the other. But if you have a certain number of these guys, then we can call it a coulomb. So what is that number? How many elementary charges do you need to make a coulomb? So the answer to that question is also on your reference table. 1 coulomb, or in my term, a bucket of charges, a coulomb is this many elementary charges. It's a huge number. It's not unlike in chemistry when we use a mole to represent a large number of small things. But this is our very large number of elementary charges, which would make a coulomb. It's on your reference table. And I'd like to try a nice little mathematical trick with you to prove a point. If there are this many elementary charges in 1 coulomb, then how much charge would be on 1 elementary charge in terms of coulombs? Okay, so let's set up just a little bit of a proportion to get that answer. So as you can see, I've simply set up a proportion of coulombs to elementary charges with an equal sign in between. Most people would suggest cross-multiplying now to figure out what the answer would be. So let's go ahead and do that to get the answer in coulombs. So I substituted the variable x in for the number of coulombs, and in my final step, I'm just going to divide both sides by 6.25 over times 10 to the 18. And after calculating, I find that x is equal to... So with that simple proportion, I was able to find that an elementary charge has a coulombic equivalent of 1.6 times 10 to the negative 19 coulomb. Now that should ring a bell because right up here I had already said that every elementary charge would have a charge of 1.6 by 10 to the negative 19 coulomb. So is there a coincidence going on or what? To solve this final mystery, I would suggest doing the following. In your calculator, I want you to take this number, 6.25 by 10 to the 18, and I want you to divide it by this number, 1.60 by 10 to the negative 19, and tell me what you get. So you should have gotten the answer 1. So what does that mean? That means that these two numbers, the 1.60 by 10 to the negative 19 coulombs per elementary charge, and this number, 6.25 by 10 to the 18 elementary charges per coulomb, it means that those two numbers are reciprocal identities of one another. Or in other words, they literally represent the same thing. Much like this bucket of charges is equal to the number of charges that are in the bucket. You could reverse think about that as the number of charges that are in this bucket are equal to one bucket of charges. Or in a final analogy, you could think of a dozen eggs. So 1 dozen eggs is equal in size to 12 eggs, but what if I just focused on 1 egg? You'd be able to see that 1 egg is really just the same thing as 1/12 of a dozen. So the 1 over the 1/12 and the 1 over the 12, those are the same thing. We're just finding two different ways of representing the same thing. And when you guys think about how many coulombs are in one elementary charge, that's 1.6 by 10 to the negative 19, or when you think how many elementary charges, 6.25 by 10 to the 18 in a coulomb, I want you to realize that these two numbers, this one and this one, those two numbers are reciprocal identities of one another, and they just are two sides of the same coin. All right, so let's just finish out this slide. What is the charge of a proton? Comically enough, this is a very straightforward answer. You'll find the answer in your notes or on this slide. So since a proton is just an example of an elementary charge, and since we have ad nauseum explained that an elementary charge is 1.6 by 10 to the negative 19 coulomb, then that means that our answer has to be 1.6 by 10 to the negative 19 coulomb. All right, so let's talk about charged objects. One thing that you need to know on this slide for sure is that protons and neutrons cannot be moved from one atom to the next, not at least by ordinary means. Now, electrically charged objects can be formed when an object which was previously neutral loses or gains electrons. So what you need to know is that electrons can easily move back and forth, but protons and neutrons cannot. And if you are an atom that used to be neutral, but you gained some electrons, that's going to make you a negative ion. Atoms that have lost electrons when they used to be neutral are going to be positive ions. Now the reason for that is because when you lose a negative charge like an electron, losing a negative is the same thing as subtracting a negative, and subtracting negatives often give positives. All right, opposite charges will exert an attractive force on one another, meaning protons can attract electrons. And similarly, like charges exert repulsive forces on one another. What you'll need to remember as a nice little factoid, however, is that neutral objects can attract charged objects of either sign, whether that is a positive or a negative charge. Let's solve this question together. Let's say that we have two neutral solids, A and B, that were rubbed together. Solid A acquired a net negative charge. What happened to solid B? Now, before you think this one's too easy and try to solve it in your head, I would like to point out some of the deep complexities that are involved in this question. The first little bit that I want to point out is that solid A and B are neutral, as the question states they have to be. And the reason why they're neutral is because the number of positive and negative charges inside each of these spheres are equal. Now, the next part of the question did go ahead and state that solid A acquired a net negative charge, meaning it was no longer neutral. So solid A, by the end of this, must acquire more negative charges than it has positive charges. Now, there are two ways to do that. It can get more negative charges than positive charges by losing positive charges or by gaining negative charges. And earlier in this slide, we had pointed out that protons and neutrons cannot be moved from one atom to the other, which means that one of these choices is not possible. In order for solid A to get an overall negative charge, like the question suggests we have to do, it may not lose positive charges. That's because positive charges, such as protons, cannot be moved from one atom to the next. Therefore, the only thing that can actually happen is that solid A must gain negative charges. Now, we know that in order for that to happen, in order for it to gain negative charges, it must be taking them from solid B. So let's say, for instance, that solid B has lost all of its negative charges and given all of them to solid A. So after doing this, we can do a quick count, and we can find that in solid A, we have 3 positive charges and 6 negative charges. Overall, this is 3 negative. That's the overall charge for that guy. And in solid B, we don't have any negative charges left. We only have the 3 positives that we started with. So overall, we have a charge of 3 positives in solid B. We might also point out that both of these objects started out as neutral, and when you take their overall charge, the -3 and the +3, you'll notice that they combine to still be neutral. This is getting at a more complex issue, which is that the law of conservation says that charge has to be conserved throughout any change. And so now the overall answer to this question about what happens to solid B becomes a really easy answer. The only way that solid A could get a net negative charge is if solid B experiences a loss of electrons. That's the only way for that to happen. All right, let's talk about the transfer of charge. Now, if a system consists of only neutral objects, which by the way does not mean that it has no charges, it just means that the number of positive charges is equal to the number of negative charges. But anyway, back to the prompt. If the system consists only of neutral objects, it has a net charge of 0. But remember, electrons can be transferred from one object to another. But the system as a whole would remain neutral as the electrons are transferred. Let's take a look at this question from the Regents. We have a rod and a piece of cloth that are rubbed together. Now the rod acquires a charge of +1 × 10⁻⁶ coulomb. What charge would the cloth acquire? Now, assuming that they were both neutral, and the rod acquires this many coulombs of positive charge, then that means that the cloth must have gained electrons from the rod. I know that the cloth gained electrons because the rod is positive, and the only way to become positive is if you lose negative charges. So that means that the cloth must have gained an equal amount of negative charges. Therefore, my answer is -1 × 10⁻⁶ coulombs. Now for this next little bit, I'm going to show you a video of a really cool parlor trick that uses a comb's static electricity to pick up neutral pieces of paper.
Hi there. Today I'm going to show you a fun little static electricity experiment, and all we've got are some little bits of paper. They've come out of a hole punch, those little circles of paper, and we've got a comb. So what we want to do now is comb that comb through my hair. Okay, there we go. Just combing the comb through my hair. Let's see what happens when we put it near the bits of paper. Woohoo! They all start jumping around and attach themselves to the comb. Okay, So there we go, the static electricity built up on the comb attracts the bits of paper and they stick to the comb.
Now, in terms of regions physics, the part that you're going to want to remember about how this could possibly happen is that, yes, the pieces of paper are neutral. They contain equal numbers of positive and negative charges. However, the negative charges inside those little pieces of paper are free to migrate towards one end of the paper or the other. And when he was brushing the comb through his hair, he was rubbing electrons off of his hair and they were accumulating on the comb. Now we know that like charges repel. So as the charge on the comb became overwhelmingly negative, it repelled all of the negative charges which were naturally inside the pieces of paper in their neutral state. So these negatives repelled these negatives, which would make all of the negatives in the pieces of paper go to the opposite side of the paper as far away from the comb as possible. And the most important part is what was left behind, which was that on the other side of the paper, we had the positive charges, which although they're not able to migrate, when the negatives migrate away, they leave positives behind. So now we have all of these positive poles on the ends of the paper that are nearest to the comb, and that's going to cause an attraction between the paper and the comb. And that is how a charged object can attract a neutral object. Now, earlier in the lesson, I mentioned that the law of conservation states that in a closed, isolated system, the total charge of this system remains constant. I had said, in other words, that if the system starts as neutral, it has to stay neutral. It has to conserve that neutral charge. So let's take a look at these three spheres. They're made of metal, which means that the electrons within them are able to flow back and forth if the charged spheres are brought into contact with one another. And there are different ways to bring them into contact. For instance, you could bring them into contact all together all at the same time, or you could do them in a specific sequence, and the results will be different. However, one thing will never vary, which is that the total charge of the system will remain constant. And in this case, the total charge of the system is -2 microcoulombs. So no matter what we do to this, no matter what scenario it is, the end scenario total charge is going to be -2 microcoulombs. But let's see what the question is asking us to do. So sphere R is brought into contact with sphere S and then removed. So R and S are brought into contact and then removed. Keep in mind that the electrons are allowed to migrate back and forth until they reach a equilibrium between the two spheres. So let's just say that all of the extra electrons, the excess electrons in sphere S that are giving it a charge of -8, let's say half of them migrate to R, and if that is the case, then what would the new charge be on sphere R and sphere S? So I was able to find that they would each have a charge of -4 microcoulombs because before R and S touch, they have a total of -8 microcoulombs between them. So after they touch, -4 times 2 is -8. So that makes sense. It means their total charge is being conserved in this system. But the question's not over yet. After sphere R and sphere S were touched and removed, then sphere S was brought into contact with sphere T and then removed. So now we have sphere S, whose new charge is -4 according to my primary calculation. Anyway, yes, sphere S is being brought in contact with sphere T, and they want to know what's the charge on sphere T when this is all said and done. So let's do that now. So from my initial calculation, I was able to calculate that sphere S would end up with a charge of -4 microcoulombs, and we're going to add that to the charge on sphere T, which is going to be, just from the diagram, +6 microcoulombs. Now, we're going to add those together and divide by 2 because that's the way they're going to divide their electrons. And right now, the -4 and the 6 are summing to a +2, So I know that overall my new answer is going to have to sum to that as well. But in any case, the -4 plus the 6 is +2. We're going to divide that by 2, and we're going to get +1 microcoulombs each for both of those spheres. Now, I know that they only technically asked me for sphere T, but this is also the answer for sphere S after it's been touched with sphere T. So +1, final answer. Okay, on this slide we're going to discuss that there are actually only certain charges that are allowed for an object, and the reason is because of the idea behind an elementary charge. An elementary charge is the smallest unit of charge that any substance can carry. Furthermore, I'd like to remind you that an elementary charge is defined as either a negative or a positive 1.6 times 10 to the negative 19th coulombs. So that means that there is no charge smaller than this charge, because the elementary charge is the smallest unit, and this is what it is in coulombs. So you can't have any fraction of this amount. You can have charges that are larger than this amount, but they have to be in exact multiples. For instance, if you had 2 elementary charges, you would simply multiply this number times 2, and you would get 3.20 by 10 to the negative 19 coulombs. Or, let's say you had 3. Then you would simply take this number and multiply it by 3 and get 4.8 by 10 to the negative 19 coulomb. But what I am saying is that if you're looking at these guys on a number line, the 1.6 by 10 to the negative 19, the 3.2 by 10 to the negative 19, and the 4.8 by 10 to the negative 19, there would be literally no feasible or even possible charge in between these two numbers or in between these two numbers. They represent discrete jumps in charge. So when we're going to solve this question down here, which a lot of people would find challenging, just keep in mind that some of these charges are realistic, meaning they represent an integer multiple of elementary charges stated in coulombs, and others are unrealistic, meaning that they contain some fraction of an elementary charge, which is simply impossible in a physical sense. So let's go ahead and get to work. Which net charge could be found on an object, meaning that 3 of these 4 charges could not be found? All right, so we'll do these step by step, starting with the first one, which says 8.00 by 10 to the negative 20 coulombs. If I want to know how many elementary charges that is, and that's going to be my tack, because if I can find out how many elementary charges it is, and it's a whole number, an integer number, then I know that it's possible. But if I'm able to convert one of these numbers to elementary charges and it turns out to be like a fraction or a decimal, so it's not an integer, then I know that that's not an answer and that that's an impossible charge. So we'll start here. Let's take this and convert it into elementary charges. So I went ahead and set up this conversion. I just took the 8.00 by 10 to the negative 20 coulombs, and I'm multiplying it by this conversion factor, which was cleverly constructed so that the coulombs in the bottom would be canceled by the coulombs up here, and that my answer would come out to be 5 by 10 to the negative 1, which of course is equal to 0.5. And the unit on that would be E, and so it's suggesting that the answer is 0.5 E, or half of an elementary charge, and we know from previous discussion that this is not possible. So it is not going to be this answer choice. So without giving too much away, I can go ahead and skip to the right answer. It's going to be this third answer choice here, but I'd like to confirm that for you. So let's multiply this by the conversion factor from above, which basically says that one elementary charge is equal in size to 1.60 by 10 to the negative 19 coulombs. And the coulombs will cancel between the initial part of the problem and my conversion factor. And then the 3.2 by 10 to the negative 19 divided by 1.6 by 10 to the negative 19 is going to give me the integer 2, and it's all the 10 to the negative 19 cancels with this down here. So you just get 2, and the unit is elementary charges. And this is what I mean by what's possible and what's impossible. So this one's possible because remember at the outset of this slide we had said that an elementary charge is the smallest unit of charge, and anything smaller than that is impossible. That's why the 0.5 in my first example was an impossible charge, and we said it was wrong. And that's why this one is considered possible, because it represents either a charge of 1e or a charge which is larger than 1e. And if you go way back up to the very, very top, you can see that I already solved this question earlier. I said that 2 elementary charges would be equal to 3.2 by 10 to the negative 19 coulomb, which was one of the opening precepts to the question. All right, last thing on this slide. What is the equivalent charge of 100 elementary charges? Assuming that I'm asking for this to be in coulombs, the answer is relatively simple. If one elementary charge is 1.6 by 10 to the negative 19 coulombs, then 100 elementary charges is going to be a number of coulombs which is, well, 100 times larger. So I can basically just take this, this scientific notation thing here and move it 100 spaces towards the 0 mark. So my answer is going to be 1.60 times 10 to the negative 17 coulombs. And if for some reason that didn't make sense to you in your head for mental math, just put it in your calculator and you'll see. Take this number right here and multiply it by 100 to get the answer. All right, Coulomb's law. Coulomb's law gives us some insight into the amount of force that 2 opposite charges could attract each other with, but it also gives us insight into the amount of force that 2 same charges could repel each other with. You can see that this equation has a very similar setup to Newton's gravitational law, the universal gravitational law. So this is an inverse squared relationship, which means that as radius increases, the amount of force between the 2 objects will decrease as a function of its square. And it also means that if you were to graph the function with radius on the x-axis and the electrostatic force on the y-axis, that it would have the inverse square shape, which looks like that. All right, so let's do an example question. A point charge of A, and the point charge A has this magnitude in coulombs, is placed this many meters, so this is going to be the radius. I'll go ahead and start labeling these. So this is Q1. This is going to be the R, or the radius. Okay, so from a second point charge of B, so this is going to be Q2. Let's calculate the magnitude of the electrostatic force that charge A exerts on charge B. I'll start by writing down Coulomb's law. Since we are solving for the amount of force, we don't need to rearrange this equation. So I'm going to go ahead and start plugging in values that I know. Now, the value for K, which is going to be the electrostatic constant, is listed here as 8.99 by 10 to the 9th Newton meter squared per Coulomb squared. So I'll add that in now. And the value for Q1 is 3.0. This was a positive number. I'm not overlooking it, I'm just not writing it. So 3.0 by 10 to the negative 7 coulombs. And Q2 was listed also as a positive number, 4.0 times 10 to the negative 7 coulombs. And we're going to put all of that over the radius squared. Now the radius was listed as 2.0 by 10 to the negative 2 meters, but of course this is squared. Now, as always, I suggest only doing the highlighted operations first, which is to say that we'll do 8.99 times 3 times 4, and then we'll divide it by the 2 squared, or 4. Now, after you do all that, you get 26.97. Now, to finish out this equation, we need to take care of these exponent values, which I'm highlighting now. So we're going to do the 9 from the 10 to the 9. We're going to combine it with the -7 and this -7. So as you combine these multiplied terms, it's really just going to be 9 minus 7 minus 7, which equals -5. But that -5 from the numerator also needs to be combined with the denominator. So when we have our, I'll just go ahead and write this down so we don't forget it. So when we have the -5 over the denominator, you need to combine this -2 with this 2. So these two multiply to make a -4. And we have now a -5 over a -4. Now when you combine the numerator with the denominator, you do that through subtraction rather than addition. So it's going to come out to be equivalent to -5 minus -4. So -5 minus -4 is the same thing as -5 plus 4, which is going to be -1. Now after all that, we can see that our answer is 26.97 times 10 to the -1. This is FE, so the answer is going to be in newtons. And this is also not proper scientific notation. So when I adjust this for proper scientific notation, I'm going to be moving my decimal point from here to there, and that will also adjust my exponent. So that means my final answer is going to be 2.697 newtons, or in terms of significant figures, I should really only be keeping 2 of these. So I suppose my final answer would be 2.7 newtons. And that's an example of how to use Coulomb's law. We have reached the pair up. I do not think I will be copying these for you. I think that I can expect you guys to copy these down yourselves. So copy down all of these questions on that separate piece of paper where your do now was. And follow it with this summary slide. Copy down all of these summary questions, and I want you to compare these two equations, for instance. And don't answer them yet. We'll answer them in class. But get all that copied down. And thanks for watching. I hope you learned a little bit about electrostatic forces. And I'll see you guys in class.